All right. Shall we get started? So actually, before diving into my presentation, I wanted to say a few words about yesterday evening's Programming Language Education Forum and some thoughts about it. Is Will here yet? No, but still having breakfast. Well, tell Will when he comes in. I really liked the presentation of his course. I think it's really awesome to see how to connect PL research to PL practice. I'd love to take that course myself. And what I thought was really cool about it was how it connects PL research to really current sort of hot developments in the software industry, broadly speaking. He's making connections to WebAssembly and Rust, and this stuff is like everyone's talking about it. And it's our community, the PL research community, that made these things happen. And I think it's a really great way to sort of make this connection that PL research matters. So I think it's really important to engage with this general idea about how best to teach PL concepts to the world at large. And ultimately, I think PL is an applied discipline. There's millions, maybe billions of people out there who are using all sorts of languages and tools to build software and hardware at scale. And what they're doing, first accepting that they're unreasonably productive at what they do. They're really, this whole stuff exists because of, all sorts of languages that some of us may like or not like and so on. But it's really our responsibility to engage with it and understand why that stuff works as well as and so to understand what makes them productive, to understand what maybe makes them not so productive, and try to sort of improve the world in that sense. I think we have a moral to do that. We're the community that's sort of at the forefront, but we have to bring those ideas back to literally soon, like maybe a fifth of the world's population using this stuff all the time. And is really kind of a mixture of natural science to understand how the world works. It's social science because it's people who are using these things, and it's engineering because we're building artifacts. And it's only math after that for me. It's math as a tool to understand these things. It's not math as a means to and an end on its own. That's a different community of people. Those are the pure mathematicians or the logicians. Programming languages is an applied discipline. And I think there's too many examples in the PL community of trying to couch its ideas in math or vocabulary that's too abstract for these billions of people to understand, to our detriment. And I think the most obvious example of this is monads, sadly, right? I mean, approximately no one understands what monads are, right? And that's a terrible failure on the part of our community. We need to find ways to explain our ideas in dead simple terms so that everybody understands it. And so as PL researchers, I think one of the most important things we have to learn and teach is first how to identify accidental complexity, or worse, sort of posturing behind fancy math. Be confident enough to call it out if we see it. And ultimately, and this is the hardest part, to simplify and eliminate that complexity. Okay? That's my take. So to put it bluntly, everything you've heard a lot of stuff in the last 2 weeks. You should be questioning everything you've heard, right? Whether it's SML or F star or Dijkstra monads or whatever, don't take it as gospel truth. Okay? Find the accidental complexity in all of this stuff, call it out, and make it simple. Okay? So that's my spiel. All right. But remember, Will comes in, tell him that I think his course is awesome. All right. So last lecture, I'm going to tell you about, I've been talking about verified implementations of different flavors. I spoke about cryptographic security, parsers, and so on. And today I'm going to tell you about the crypto primitives themselves and how we implement them and make them go fast and do it correctly. It's about a library called EverCrypt, and I got these slides from a couple of my colleagues, Jonathan and Chris, and messed with them, so any errors there are mine. Broadly in the Everest Project, we're building this stack that's providing an implementation of TLS 1.3. I told you on Monday, on the first two lectures, about this parsing component called EverParse. I told you a bunch about how we model cryptographic security and do equivalence proofs and all this. And today I'm going to tell you about this piece, which is the crypto library that underlies this stuff. So EverCrypt is a cryptographic provider. So what's a cryptographic provider? It's a collection of algorithms that implement various primitives like hashing and encryption and so on. And it needs to be, in a sense, nearly exhaustive, because you need to be able to use this library to negotiate connections with the rest of the world, and they may be using a whole variety of algorithms. So you need to, a provider needs to have coverage of algorithms. It needs to provide several implementations of each algorithm, targeting different hardware and so on, because this is also on different machines, different implementations maybe are the most efficient and so on. So it has to multiplex between implementations. It needs to sort of group APIs by family. So, for instance, there may be many implementations of many different hashing algorithms, HMAC SHA-1 or SHA-2 or SHA-256 and all these things. They, at some level of abstraction, they're just hashing algorithms, and a provider needs to sort of abstract over that rather than leaking details about the algorithms through the API. And this whole thing has to be sort of packaged in an API that's easy to use. For instance, before picking a particular implementation for certain hardware, it needs to detect what machine you're on, and only then enable the use of certain instructions, because otherwise, if you try to run it on some other machine, your machine will just blue screen. So in a way, a cryptographic provider is really an essential piece of software. It's beyond secure communications. It's used for all sorts of things, like, you know, almost every app these days needs some crypto. And there are many cryptographic providers out there. The biggest one is OpenSSL. Now, OpenSSL, broadly, if you think about it, OpenSSL has two primary components. There's a component called libcrypto, and there's a component called libSSL. And libcrypto implements crypto algorithms, and the other component implements the protocol stack. And libcrypto is the crypto provider. It turns out that libcrypto is nearly like more than half the code of OpenSSL is just implementation of crypto primitives. They may have like a dozen implementations of an individual algorithm, tuned to various architectures and so on. There are several others. There's libsodium is trying to be a simplified crypto provider. It's gaining traction. It's provided in many languages as the default crypto provider. And there are several others, including, this is Windows. Windows BCrypt is the Windows crypto provider. It comes on every Windows machine. It's in the System32 folder. This thing is always there. And EverCrypt, that's ours. So maybe a brief reminder. Why should we bother verifying cryptographic algorithms and their implementations? Well, because roughly, you know, things sort of, the way crypto primitives are designed and implemented, it goes in several stages. So first, there's some mathematics. So for instance, AES-GCM, which I mentioned a couple of days ago, is an authentication code, and it's used by nearly 90% of all TLS connections. And essentially, it's doing multiplications or operations in a large finite field. And there's some math about it. Okay? That's the math in some sense. Okay? And then there's tons of documents issued by different people, including Intel and so on, that describe how you're supposed to implement this math. And that's kind of the algorithm in some sense, okay? And then people go off and they write a bunch of code. They write a bunch of assembly. And this is kind of like the reality of some, hundreds of lines of assembly instructions, supposedly implementing the algorithm that implements the math, right? And, what could go wrong, right? So things do go wrong. And if you look at, bug reports over the years, they're quite regular. This is a bug in an implementation of a particular elliptic curve in many different providers. OpenSSL had bugs in this this Mac Poly 1305, and they produced the wrong results. And in a way, this kind of code is really hard to test in some sense. They're designed to be sort of cryptographically, they're sort of designed to be sort of random in some sense. So like exhaustively testing them is really like a non-starter. So in some occasional inputs, they forget to propagate carries or something and produce the wrong result. And even AES-GCM, this most widely used thing, has had implementation bugs in it. And just 2 weeks ago, just to say that this stuff keeps happening, 2 weeks ago, there was a crypto library that was a infinite loop in one of its algorithms that could be triggered by presenting to a machine a carefully crafted X509 public key certificate. And you can mount a denial of service because of this infinite loop. So there's bugs in this stuff all over the place. So of course, our hammer here is let's use program verification to make sure to root out all these bugs, right? So essentially what we do is we have the math. We have an algorithm that supposedly implements the math, and we do a proof that says this algorithm refines the math. And then we have our low-level implementation in C or assembly, and we prove that that thing refines the algorithm. So so that's maybe just illustrating that in some more detail. We write a spec in F star that you can't really see it, but it's sort of a very compact spec. In one line, this is GF128 modulus load terms. That's a modulus in this field, Galois field of 2 to the 128. And the spec fits in one line. And this is an executable spec. It's just functional F star code. So you can extract this code to OCaml and test it. And we test it against test vectors to make sure that we got the spec right. And then we write an implementation blueprint. This is kind of a transcription of the algorithm that's described as an implementation strategy, and do a proof of that this refines that. And then we have 2 tools in which to do these to do the low-level proofs. There's Vale, or Verified Assembly Language for Everest, that lets you do assembly implementations and show this refinement proof here, or this DSL called Lodestar for C implementations with a refinement proof there. And then you can extract this. Vale is just a deeply embedded assembly language in F star. I'm going to tell you more about it. You can just print the assembly in a concrete syntax of your choice, or extract via Kremlin to C. Okay? So what's actually verified? So first, safety. So as a baseline, if you don't have a memory and type safety, you can't really prove any of the rest of it. So broadly speaking, if you think about what a functional correctness proof involves, it involves showing that the raw bytes in memory that you're manipulating correspond to some mathematical object that that's your spec. And if you have if you don't have memory safety, for instance, you're reading off the end of a buffer, then essentially, as far as the spec goes, it looks like you're manipulating junk bytes. So you're never going to be able to show that these junk bytes that you're manipulating actually corresponds to some mathematical object in some sense. So safety is a kind of a prerequisite for everything that comes after it. So we prove memory safety in the sense of spatial and temporal safety, preventing these kinds of particular attacks. And then functional correctness, that's the refinement proof. And then secrecy, which is to show that for instance, we prove constant time properties. The implementation of a crypto primitive, its execution time or its execution trace does not depend on the secrets it's manipulating. Now, to be clear, we're not trying to invent new implementations of crypto algorithms. There are smart crypto implementers out there who come up with strategies for how to implement interesting crypto primitives in, say, constant time, never branching on a secret. And what we do is we take their implementations and we actually prove in F-star that whatever measures that they've employed are actually sufficient to prove constant time, for instance. And since everything is in one language, but from the math to the implementation, the spec and the implementation don't drift because they're all connected together. So we released this library, and we got a bit of press around it. And a reporter on Quanta magazine had that headline. We didn't choose the headline. And sure enough, we got a lot of, this article came out, and then the internet, like many people, were like, of course this stuff can be hacked. This is snake oil. What's this stuff? And Bruce Schneier, who's a famous security blogger, was like, overhyped article. Does this sound like snake oil? I mean, and thankfully, Schneier is, look at what we did and then says, oh, well, actually, what we say about it is more measured and accurate. It's actually pretty cool and so on. But there's actually a kind of a bit of a danger around this of program verification work, sort of, at least in the way it's presented, kind of overhyping what it may actually provide you with. And when you write when I would hope that if any of us were to write a paper about this stuff, we're very careful about what you trust and what the attacker model, and should be careful to not. I mean, going back to my original the prefix, the prelude to this lecture was talking about trying to simplify and remove accidental complexity. Well, you shouldn't simplify too much and reduce the whole thing to just one bit, right? And saying, whoa, this stuff can't be hacked, right? That's not okay either. So will our code be perfectly secure? Clearly, no. Okay. So our models make many assumptions. For instance, all this proof about security only works if the signing key is actually kept private. If by some other means you leak the key, then this constant time or whatever is completely irrelevant. Our models may not be complete. So we have some model of the architecture, and we prove constant time against this architecture. But our models stop somewhere. So for instance, we don't consider microarchitecture, and maybe things like Spectre and Meltdown and Rowhammer and so on could be used to exploit some of this stuff. In a way, we build our models to capture a broad class of attacks that span many attacks or at least all the attacks that we knew of at the time of writing these models. And if tomorrow somebody comes up with some other, some other way of attacking a system, maybe there's like you exploit quantum effects or something, our models don't capture that, right? And then finally, all these mechanical verification depends on about the tool. So our tool chain may be buggy. Our trusted computing base includes Z3. It includes the Kremlin compiler. It includes the C compilers that you use downstream, and it includes F-star itself. And we work on trying to reduce that in several ways. For instance, on an earlier version of F-star, there's a POPL paper, maybe POPL 2011 or something like this, where we certified the F-star compiler by bootstrapping it in F-star and then checking the bootstrapping using a proof term that we checked in Coq. So we bootstrapped the correctness of the F-star compiler using a proof in Coq. That was in 2011. We haven't done that again for our most recent version of F-star, and there are surely still bugs in it. Okay, so it may be hard to trigger those bugs in one of these proofs, but I wouldn't be surprised if there's still a bug in it. We find them and fix them routinely. So yeah, so it's important to take all these verification results in context. These are not perfect results. Okay. But that said, despite all this, doing computer-aided verification has several advantages. The whole thing is checking a proof does not involve any human intervention. You have to read the specs, of course, but checking the proof is automated. It can take, for a full build of Everest these days takes about an hour and 20 minutes on 40 cores. Okay. It's compositional, so once you do a proof of one component, you can use it as a building block in another component without having to recheck its proof. And the whole thing is maintainable. So in a way, if you, in a traditional software development, if you change one line of code somewhere, you may test it locally, it may pass its test, but you have no idea how it's going to ripple elsewhere. The change is going to impact other things. But with proofs, you know exactly what the interactions are. You can change stuff and be confident that your change does not ripple to places that you don't know. Questions so far? So what does EverCrypt look like under the covers? So one way we see it is kind of as a like a no excuses industrial grade library with full verification. So one of the bars, I think I mentioned this perhaps in in the first day, was that any algorithm that we add to EverCrypt, our informal bar is that its performance must be at least as good as the best algorithm out there. It's implemented in a combination of assembly and C, and every time you have to call from C to assembly, there's a bit of interop that you have to go through, and that interop is also verified. So we prove that C and assembly interoperate correctly. And it covers, at the moment, it covers that suite of algorithms, and that's actually may look like quite a lot, but it's actually a small subset of what OpenSSL actually does, and we're on this kind of train of trying to capture the long tail in some sense. Right, so like I mentioned at the start, we verify multiple implementations, and we include things like auto-detection of CPU features, and so on. I think this is mostly a repetition. And maybe I should say a bit about agility. So this is the bit where we allow clients to switch between different algorithms. So for instance, crypto proofs, the way they work, broadly speaking, is with respect to hypotheses security of certain constructions, right? I mentioned that earlier. So for instance, we may assume today that, I don't know, SHA-2 is a good hash. And our security proof at the end would be something like, well, assuming that SHA-2 is collision resistant, then you get some property. But it's very likely that 5 years from now, SHA-2 will no longer be a good hash, or maybe 10 years, I don't know. This happened in the past for other hashing algorithms. So we should expect it to happen again for the algorithms that we have now. In a way, it's all just a cost game, right? I mean, if you're willing to spend enough computational resources, you can break these hashes or encryptions. The question is, at what point is it is this cost justified? And as hardware gets faster, this cost goes down. So eventually, these hashing algorithms or encryption algorithms will be broken. So the way these protocols are designed is to be, and the technical term is like to be cryptographically agile. So in a sense, I can negotiate a connection saying I'm going to use a particular hash algorithm, And the rest of the protocol is parametric in the choice of this hash algorithm, so that the same protocol can be used again with a different hashing primitive when that becomes necessary. So for that to be supported, the API that provides you with an implementation of hashing should also be suitably parametric. And realistic crypto providers are designed this way, and so EverCrypt has to also be designed this way. And it allows clients to sort of switch between different implementations of hashing algorithms by just configuring it appropriately. But from the perspective of the API, all hashing algorithms are equivalent. So making this work also involves, so I wanted to highlight an implementation of, this is curve 25519, which is a particular elliptic curve. We have an implementation of it that uses a mixture of C and assembly. And doing this combination of C and assembly is really important to get it to go fast. And I think at this point we have the fastest implementation of curve 25519 out there because we do this fine-grained switching. And I see EverCrypt as kind of it's a verified crypto provider, but it's a foundation on which you can build other verified applications. So given this crypto provider, we build, for instance, a fast incremental Merkle tree that we use that's used in Azure's blockchain. So blockchain ultimately is essentially a Merkle tree, and so we have a verified implementation of that. There's Signal. libsignal is a messaging protocol. So if you're using WhatsApp or Skype private conversations or Signal itself, you're using the Signal protocol. And we have an implementation of Signal on top of EverCrypt that's verified. So EverCrypt is kind of a foundation on which to build this stuff. The whole thing is actually quite big. There's maybe 7,000 lines of C code, and that produces about that much C code, 23,000 lines of C code and 18,000 lines of assembly code. After a bunch of specialization and normalization and erasing proofs, but kind of doing a lot of inlining. So I'm not sure how you should exactly count this number. Some of it gets erased, some of it gets duplicated. So, all right. So I think what I wanted to do for the next bit is actually tell you a bit about how Vale works, which is this assembly language. I've told you over the last few days about how this kind of C subset of F-star works, but here's a bit about Vale. So I think I showed you this slide on the first day. We have a fast implementation of AES-GCM. And the way AES-GCM works is that it has to do several optimizations. Essentially, it's doing, in a pipeline, additions, multiplications, modulus operations in this 128 field. And to get this to go fast, you have to do various things like the mods are particularly expensive. So you have to kind of delay the mods and then try to parallelize this as much as you can using like careful instruction scheduling. And then you can get it to go fast. And some of these things involve using, Intel has special instructions for doing carryless multiplies. And that instruction was added to Intel's instruction set primarily because of AES-GCM. So in order to get it to go fast, you have to be able to tickle this particular instruction. And that you need to go to assembly. So the way Vale works is, Vale is a DSL. It has its own front end where you write assembly programs in a imperative syntax that looks like some idealized assembly with instructions like this, moves and adds. And you can write horse-style specs for them by saying, this is an assembly procedure, it has this precondition, it has that postcondition. And then what you do is, the Vale tool is an untrusted tool that translates Vale deeply embedded assembly syntax for into F star. And now F star verifies this deeply embedded syntax. Okay, and what you trust is the model of assembly semantics in F star. So we give an operational semantics for assembly in F star, derive a Hoare logic for it, and then prove this deeply embedded program correct. And then once it's proven correct, so the way the proof works is that we build verification conditions for it, and then if you verify the program, we can, do I have that there? We just print this deeply embedded syntax as GCC assembler, let's say. Okay? So let's look at what verification conditions for a simple assembly program ought to look like. So let's say I have this. I have a 3 instructions, move, add. And I want to prove that at the end, the value of the RBX register is 3 times the value of the RAX register, given that the initial value of RAX is less than 100, so that I don't overflow, essentially. Okay? So to prove this, I should get a verification condition that looks like this. And each implication you can see as being corresponding to each instruction. So here, so this is my precondition, RAX 0 is less than 100. And then here I'm going to say that after this move, the new value of RBX, RBX1, is equal to the old value of RAX. And under that hypothesis, I need to prove, this is an add, I need to prove that the addition of RAX and RBX does not overflow. And under that, if I can prove that, I can show that the new value of RAX is equal to that sum, and then prove the continuation. And then the second overflow, that's the move corresponding to the add, and then I have to prove the final post condition, that RBX is equal to 3 times RAX. Okay? So that's what you'd like to get. This is kind of the simplest, cleanest verification condition that you would like to get for this program. But if you just translate this naively to F star, and you get F star to infer a verification condition for it, this is the verification condition that F star will produce. I don't want you to read it, but it's a mess. So what's happening is that essentially what we've done is we've embedded an assembly language into F star with an operational semantics for it, and now we want to reason about programs in this embedding. But as we infer verification conditions for it, the verification conditions leak too much information about the embedding. So rather than verifying, what we'd like to be thinking about is verifying assembly programs, but F star produces a VC that looks like verifying the embedding of assembly programs. So this verification condition contains stuff in it like little artifacts about the evaluation semantics, eval operand, and that the representation of machine instructions as a list, and all this stuff that is ideally should be beneath the level of abstraction for when reasoning about assembly programs. This is a leaky abstraction, essentially. So what we want to do instead is to kind of write. And one way to do it could have been, well, we'll just write our own VC generator for Vale. Say the VC directly to Z3. And we have to trust this tool, and we can't really interact with F star libraries for math and whatnot. This is kind of a separate thing. Chris says F star would be lonely and sad, which I suppose so. If we did it this way. So instead what we're going to do is to make F star happy and go this way by writing a VC generator for Vale within F star, prove it's sound in F star, and build a VC by running F star's normalizer on the VC generator encoded in F star. And then feed that to Z3. And this way, this tool, that's this ad hoc front end, is not part of the trusted computing base. And you can use F star libraries, and you can get the kind of compact VC that you actually want. Generator. So there's some choices. We needed some way to represent the program. Well, string, well, hopefully not. We can use a nice data type of a deeply embedded representation of an assembly program and its verification conditions. How should we produce ultimately D3 kind of as a big string, but we don't want to produce it as a big string. So if we played this game again, you might say the obvious thing is, oh, let's build a verification condition as a star. But what this would do would be to say, okay, we need to interpret the semantics of a piece of syntax, that's these instructions, as a data type, which is a piece of syntax. And then if we get this piece of syntax, we then, in order to prove that the VC generator is sound, we'd have to give an interpretation to that piece of syntax, these verification conditions, as something semantic in F star. And that's so instead what we're going to do is we're going to go directly from syntax into a denotation. And our representation of verification conditions in F star is going to be just an F star term. So we're going to use a bit of dependently typed programming here. We're going to go from a data type, from some syntax directly to denotations. All right, so let me show you how this works in a small demo. All right, so this is, maybe make it bigger, right? Big enough in the back? Okay. So this is mini Vale semantics. It's kind of a tiny version of Vale, just for to give you the general idea. So here, what we're going to do is we're going to have a deeply embedded syntax assembly language of an assembly language that has just two instructions: a move and an add, and 4 kinds of registers: RAX, RBX, RCX, RDX. Okay, and a program is going to be either a single instruction, a block of instructions, and I added one kind of structured control flow, a while loop. Okay, and that's all there is. I'm going to represent this my program as a map, registers to words, NAT64s. A natural 2 to the 64. Okay, so it's and then I'm going to define I don't know, I'd like to think of it as a totally standard operational semantics, BigStep operational semantics, as an interpreter for these instructions. So this interpreter comes in 2 pieces. There's evaluating individual instructions. It's got an evaluator for move that's going to update the register. And it's got an evaluator for add that's going to do the add, mod 2 to the 64, and update the register. And these two other instructions are, in a way, invalid. So that's like trying to do a move where the operand is not a register. And in that case, the machine just steps. In our real implementation of Vale, this evaluator comes with preconditions to ensure that you're never in this unknown state. But here I'm just going to step to an unknown state. And then I have an evaluator for code that's essentially going to evaluate instructions, blocks, and while loops. And this while loop, to evaluate it, I'm going to fuel the evaluator so that I can actually show that it terminates. Okay? So when the fuel is 0, the while loop just stops, and the thing returns none. Questions? It's again pile of concrete syntax, so you guys might have questions. Great, maybe you're internalizing F star syntax. That's amazing. So that's our trusted semantics. Everything up to here is part of the spec. Okay, and now we're going to try to build a small horror logic for it and build a VC generator for it. And I'm going to try to do this in a maybe a way that's slightly unusual than what you might do, like as a textbook way of building VCs. So first, I'm going to prove a couple of lemmas. I'm going to prove that the fuel is somehow irrelevant for the semantics. It's just there as instrumentation. So what this is saying, I'm going to prove a couple of lemmas that if I evaluate a piece of code with some fuel, and it successfully returns some final state, then if I increase the fuel, the evaluator is still going to produce exactly the same state. And then I'm going to write a function that lets me kind of compute the fuel needed to execute a sequential composition of terms. What this is saying is that if I want to evaluate the sequential composition of C with C's, and I know that evaluating C required F0 amount of fuel, and that evaluating the tail required some Fm amount of fuel, I can compute the amount of fuel required to evaluate their sequential composition. It turns out to just be the max. Okay. And now I'm going to build a verification condition generator for it. So I'm going to try to compute weakest preconditions for this little language. And weakest preconditions are just transformers from postconditions to preconditions. We've seen that before, right? And postconditions and preconditions, in this case, these are pure commands. They're not returning any result. So a postcondition is just a predicate on a state. And the precondition is the same. And here's my main judgment in some sense. Has WP. C has WP. WP is the main judgment of this logic that I'm defining. And its interpretation says that if you take any postcondition K and some initial state, then has WP is ghost, meaning this is just proof. It's just computationally irrelevant. It's just a judgment in some sense. And but it's going to compute, this relation is going to compute the final state and the fuel needed to actually run this code successfully. And it's what it says is if you can prove the weakest precondition for that postcondition in the initial state, then you can run this code with the computed amount of fuel in the initial state. It's going to successfully terminate in the produced final state, and this final state is going to satisfy the postcondition. Okay? And right, so now here's a high-level idea that's going to tell you how I'm going to actually compute WPs. So I want to do two things when computing WPs. I want it to be extensible, so that if I add new instructions, I can still reuse the same framework. Compact. I want the WPs that are produced to be as like the ones I showed you on the slide previously, to not leak too much about the abstraction. And the way I'm going to do this is by defining a kind of a type class that packages with a piece of code the WP for that piece of code. Okay, and then I'm going to define my WP generator in a way that says, given a type class instance for the instructions I'm evaluating, I can build a WP for the control constructs over these type class instances. So the type class is a class that I'm calling with WP, and it's packaging a piece of code with its WP and a proof that says that code actually has that WP. Okay? And I'm given this on an individual instruction, I can build an index type, a kind of an inductive family that's going to, for a list of instructions, is going to package a list of instructions with the WP generator for that list. And this is, it's kind of you can see this kind of like a vector indexed by a list. So if I have empty instructions, then that's easy. If I have a sequential composition, then I need to have a type class instance for the head and instances for the tail, and I can build an instance for the composition. And I'm going to add one more interesting construct here, which is these two are just for the raw instructions that I'm trying to evaluate. But I want to inject into the program that I'm evaluating a way to add lemmas, sort of do a proof about the program that I'm actually evaluating. Right? For instance, if I'm trying to verify a chunk of code C's, I can inject a lemma in my instruction stream that's going to show an implication between some pre and a post condition, and I'm going to verify the instruction of this lemma. So adding a lemma does not change the instruction stream, but it's just a way to sort of inject some proof in the middle. Questions? Yeah.
Is there a reason that you don't mark this ghost somehow as like computationally relevant?
It's a type. It depends on how you use it. So it's you can use it in a computationally relevant way if you want to, but in this particular example, I will not. Yeah. Good. Sorry, I meant to tell you that in the beginning. So I started at the very top. So what I'm going to do is I'm going to show you how this works towards the end. But essentially what I'm going to do is I'm going to build a VC generator, and then I'm going to try to get the F-star normalizer to reduce it. And I'm going to have to configure the F-star normalizer with a particular reduction strategy. And this reduction strategy I'm going to use is going to say, hey, unfold only very specific terms. And the way I'm going to mark the terms that need to be unfolded is to tag it with this attribute. So again, I think that's a question that someone, I forget, maybe he's not here right now. This is like kind of how SMT interacts with normalization in some sense. And F-star gives you a number of sort of knobs to control it, and this is one of them. So I have my type class instances, and now I can define my VC generator that says if I have this C's is an instance of this type class. Then given a post condition K, I'm going to compute a precondition by recursively computing this function. If the instruction stream is empty, then I just have to prove the post condition on the current state. If I have a sequential composition, then what I'm going to do is, I left some comments in there. This is an easier way to see it. Hold on. Okay, I'm very bravely doing this in the middle of my demo. Let's see if it works out. But to compute the VC generator for a sequential composition, I push the post condition through backwards, right? So you push the post condition through the tail using the VC generator. You get a precondition for the tail, and then you push the precondition of the tail through the head instruction and apply it to the initial state. So those are the two main cases. And here you're going to see how this lemma actually works. So if I have a lemma in my instruction stream, a lemma in my, it's not technically an instruction stream, but it's a lemma in the program I'm going to verify, then the way VC looks is essentially this thing is adding a. So it's saying if I'm trying to verify these instructions and I have this lemma, then prove the precondition of the lemma and use the postcondition of the lemma to prove the weakest precondition computation. So it's weakening, it's sort of altering the precondition to be this one and using the postcondition to weaken the weakest precondition. And now I'm going to prove my VC generator. And the soundness proof is saying that if the VC generator computes a precondition that's provable, then code producing a final state that satisfies the postcondition. Okay. And another way to read that spec is like this, that this block of instructions has a WP corresponding to that. Okay, so now I'm going to give some instances. So that's my VC generator done. Now I'm going to have to give instances for the particular instructions I'm interested in. So here's a, so for instance, well, this is the type class instance for move. Okay, and I'm not going to show you in detail, but it's, you can imagine what it is. The move is sort of like the substitution rule from the whole rule I showed you yesterday. You give an instance for add. And now I'm kind of done with the VC generator. Now I get to this point of like, I actually want to run the VC generator using F star as normalizer. And here, F star gives you this, a little bit of a way to tag a term, X, with an attribute that's called, that's going to define a normalization strategy for that attribute, for that term. So norm, with all these directives here, says normalize the term here using this reduction strategy. And this reduction strategy is going to, iota is pattern matching, zeta is fixed points, simplify formulas, evaluate primitive operators, unfold all terms that are marked with Q adder, that's what I was mentioning earlier, and additionally unfold all these other terms, and only those. So once I rig the normalizer this way, I can say, hey, if I want to prove some, I can normalize the VC, and that still produces a valid VC. Now, to verify a simple program, this is the program that was on my slides. I do a move and two adds. Given such a program, I can build a type class instance for that program by essentially packaging up the instances for the individual instructions. And then I can do a proof. So let's see, and I can do proofs in kind of two ways. So here's a naive proof. A naive proof says, I'm trying to prove that those three instructions satisfy this triple, that in an initial state where the value of RAX is less than 100, if I evaluate the code, I get a final state in which the value of RBX is 3 times the value of RAX, and I say something about how the state changed. Okay? And I can applying the whole rules for individual instructions by doing moves and adds, and then trying to merge the fuels up and so on. This is kind of a manual proof. And F star can do this proof, but it's kind of a bit of a tedious proof that produces these kinds of ugly VCs. And instead, another way to do the proof is just to do it like this. That's the same spec I showed you before, but the way I'm going to do the proof is just by running my VC generator on it, on the instruction stream. This is the instruction stream that contains the codes. This is the type class instance for that instruction stream. That's the post condition I want. F star just reduces it and produces a formula. It feeds it to Z3, and the proof is done. So that's.
To be clear, the reason this goes through so well is because of the normalization that you manually.
Right. I kind of said I'm going to do most of the proof. I'm going to do the VC generator proof by reflection in some sense. I'm going to operate over the syntactic representation of terms, compute a formula that's going to reduce as much as I can, and then I'm going to, whatever's left over, and only what's left over, I'm going to feed to Z3.
So if you're comparing this to Coq, would you say that you basically attach your, rather than attaching the tactics to your proof, you're attaching them to your terms in a way that allows the proof to go through automatically?
Yeah, that's one way to do it. Yeah, one way to see it. You could have also done it the other way. So I did it attaching this norm. But you could have done it also by sort of trapping the VC using tactic, and explicitly saying, oh, normalize this term using a tactic and then feed it to Z3. Yes, you could also do that. Yeah. Yeah. In this example, I don't use a lemma. So the lemma would look like, let's say, So for instance, suppose Z3 did not know about arithmetic at all, right? Now here, the program, what it does is, let me go back to the program. The program is doing a move and two adds in a very intentional way. What you can see is that the final state of RBX is equal to two additions of the initial state of RAX. And then Z3 does a proof that says, well, RAX plus RAX plus RAX is equal to 3 times RAX. And that bit requires arithmetic reasoning in Z3. Right? Now, suppose I did not have arithmetic reasoning in Z3. Then I would have to justify that identity somehow. And that identity would be justified by a lemma.
Oh, I see. Some domain-specific.
Yes, for instance. But it also could mean things like, well, essentially some step of the proof that cannot be automatically found. You can inject a lemma to Sorry, nested?
You have a loop.
Yeah.
Right?
Yes.
They handle
Nested while loops? Yeah, I think so. I mean, I think this syntax allows it. So if you go back here, the body of a while loop is just code. So it can also contain a while loop. Right? Okay, so that's kind of that part of the demo. I have a second demo coming up. Now, let's say, so I hope you can kind of have a rough idea of how we end up verifying. Okay, now I have take this example of curve 25519. We have a bunch of C code in this low star DSL. And there's optimized Vale routines for fast multiplications. That's in this particular curve. And I need to call from C into Vale. And the way we do that through an interop layer that's going to interpret a Vale specification and proof as a low star proof so that I can actually make this call and make the interfaces match precisely. So here's a second kind of quick demo, which is how we actually do interop. So I thought some of you may be interested in this from, for instance, Amal was talking about compilation and how compiled programs in one language. And this has at least a little bit of that flavor. You have a C program, and there's an assembly program that came from somewhere else, and they're trying to get them to interop. And what we're going to do is to, in our full implementation, getting this interop to work out well has a couple of delicate. There's things like the calling convention. There's the assembly program expects its arguments in some registers, and if there's too many, then they spill onto the stack, and all of that has to be specified precisely. And then there's a difference in their memory models. From the perspective of the C program, you have a structured memory model that looks kind of like the ComCert memory model, where you have, it's kind of like a typed view of memory in a way that says that, essentially blocks of memory have, one way in which you can think about it is that two different pointers point to different points of memory kind of have infinite distance between them. There's no way you can overflow one buffer and reach the next one in some sense. Okay, so that's kind of a typed view of memory. But at the level of Vale, this is just flat. At the level of assembly, it's just the memory just looks like a flat array, and we have to somehow move between these two levels. So reconciling differences in the memory model is another part of this interop layer that we have to do. What I'm going to show you in this demo is kind of the style to do it, which is, and in this demo, I'm just going to show how we move between. We handle the calling convention. I'm not going to show you the memory part, but I think what I wanted to emphasize about this is that there's probably too much detail for me to show it to you in here. I think one part of this that I think is kind of cool is that we're going to do this interop of generic programming, where generic programming, and I mean it in the sense of we're going to compute the calling convention based on the arity of a Vale program, which is going to be some natural number, and we're going to interpret that arity as a type. So we're going to compute an arrow where the number of arrows depends on this NAT in some sense. Okay, so let's see. So where shall I start? So as before, I have 4 registers. Names changed in this demo. Okay, but I have 4 registers, and there's a way to interpret a Vale precondition. A Vale precondition is a predicate about all the arguments in scope, and then some property about. So I have to interpret, given a particular arity, I'm going to interpret a Vale precondition as an arrow with n arguments, and whose return type is a predicate on memories. Yep. N arrow, sure. So here's an arrow. This is the bit of, this is the kind of stuff that, I think, this is the kind of things you can do with dependent types, right? So you can say, I have an n arrow. An n arrow is a recursive function on a natural number. And and it's computing a type. And if n is 0, the type is just the result. Otherwise, it's an arrow whose domain is a UN64, because registers are UN64s, and whose codomain is an arrow. And you're computing a type by recursion, right? It's kind of maybe the kind of canonical example of this kind of dependently type generic programming is print. So the printf takes a string, a format string, and depending on the contents of the format string, it computes a type whose arity and values depend on the format specifiers. And this is kind of that style too. It's saying I have a natural number, and the natural number is going to determine my arity, and all the arguments are just UN64s. Yep.
So is there some way you're expressing this depending on the stack?
In this demo, no. But in the real thing, yes.
So where would that go? Would that go into an arrow?
Yeah, so n arrow, so this is one part of it. Now I'm going to show calling convention. Ultimately, what I want to do is to say I'm going to take a Vale signature, and I want to interpret it as a low-star signature. Okay, and what this involves doing is I'm going to have to take an argument that low-star processes in, and store it in some particular register according to. The ith argument in this demo goes in the ith register. Now, the real thing, like depending on the architecture, there's a different calling convention, and Linux and Windows do different things, and so on. And this thing has to specify exactly where the arguments go. And in case there's not enough registers, this wrapper would say, okay, the 5th argument goes on the first stack slot. But sorry, I kind of jumped ahead. But a Vale signature is a Vale. This is the type of the Vale interpreter on a sequence of instructions, where given an initial state, it produces a final state, where the precondition is this n-ary Vale precondition, and the postcondition is some n-ary Vale postcondition. And I'm going to map between the two. Whereas a low-star signature actually takes n in the low-star memory model. And I'm kind of bridge the gap by doing these wrappers. So I think it's kind of all I wanted to say about it. If you have more questions about this, yep.
So I'm understanding you're interpreting brain postcondition and low star.
Yes.
And then do you show that when you go back again to Vale,
Yep.
the preconditions are stronger than the preconditions
Yes.
you started, and
Yes.
the conditions are weaker?
Yes. So given a Vale proof about some sequence of instructions, if I want to call it from low star, I have to wrap it with this gadget, and it's going to then effectively say, okay, whatever Vale property I had about the Vale machine, I'm going to interpret it as a property about low star, such that proving the property about the low star machine implies the Vale one. So the two have to match up. Yeah. Other questions? Okay, so some conclusions about this part of the work. So we have a fast verified implementations of assembly language implementations of various primitives. We kind of use F-star as a proof assistant to build VCs efficiently using normalization and SMT. We bridge between low star and Vale using these interop layers. So the last 10 minutes, I thought I'd just wrap up quickly telling you about, where I see this kind of EverCrypt work going in some sense. So one way in which you can use EverCrypt is kind of just do this sort of cherry pick approach. And this is, for instance, the Firefox and the Linux kernel do this. They say, okay, Everest is producing these verified implementations. They have their own crypto providers, but they want verified implementations for individual. They don't take all of EverCrypt. They just take one verified implementation and stick it into their providers. Okay. I think Fiat Crypto is another project from MIT that has a similar kind of flavor. They're producing verified implementations of elliptic curves, and say boring SSL is picking up individual implementations. Actually, this is an interesting quote. Maybe I can read it a bit. This is from a Linux blog where they say, this project takes the approach of modeling the algorithm in F-star and proving the model correct, which F-star is designed to optimize. Then, in a term of art which never fails to make me think of Arnold Schwarzenegger's Terminator, descending into a bath of molten metal, the model is lowered into C, or in some cases all the way into assembly language. So if that's what you need to do to kind of, make this appealing, then sure. Another way you can do it is to kind of take the whole library in some sense. You take our whole crypto provider and just use it. And some blockchains are beginning to do this. Concordium and Tezos kind of just use our provider. Then you can kind of extend the algorithms to it. So one thing that we're looking at right now is post-quantum crypto. So the context here is that the community at large is quantum computers becoming a reality. And NIST, the standards body, has a competition at the moment to standardize on various post-quantum crypto implementations. These are cryptographic constructions based on mathematical primitives for which there are no known efficient quantum algorithms. And they're trying to standardize on these algorithms now, because the danger if a quantum computer becomes a reality, what may happen is that someone who's recording internet traffic today can, with a future quantum computer, decrypt today's traffic. So even though a quantum computer may be quite some ways out, it's important to sort of start migrating to using quantum-resistant algorithms fairly soon. So we have implementations at Microsoft, we have a team of cryptographers that's participating in this competition, proposing new post-quantum implementations. And interestingly, participants in this NIST, folks from our team, see verification as actually kind of an important part of actually competing in this competition. Verification is seen as being a differentiator for entries in the competition. So we have a verified implementation of this algorithm called Frodo, and we're working on another one right now. And then I kind of see it as beyond just doing individual crypto algorithms. I see EverCrypt as a foundation for building more verified software. So we're interested these days in a protocol called Quick. Quick is a protocol from that is being standardized in the IETF, but it started as a protocol that was being pushed by Google called Speedy. And in fact, if you connect to YouTube, let's say using Chrome, you're probably using some version of Quick. And the idea with Quick is that latency on the internet is actually, for secure connections, is actually a real problem. So let's say I'm connecting, especially if I'm on a high latency network. Let's say I'm connecting to YouTube using a 3G network on my phone. Then the number of round trips I make to YouTube actually is a multiplicative factor on the latency. So I want to negotiate a TLS connection with YouTube. What happens is that it's TLS on top of TCP, so there are TCP round trips. And once I have a TCP connection, then TLS actually has, TLS 1.2 has 2 further round trips to negotiate keys before you can start sending the first interesting application message. So there's a move to try to reduce these round trips, and Quick is kind of the most aggressive one in this space. So what it's doing is it's taking TLS, and instead of running it on top of TCP, it's kind of squishing the stack, the networking stack, and running TLS directly on top of UDP. Which means that implementation of Quick has to deal with, well, it has to deal with crypto, but it also has to deal with congestion control and reorderings, and it's like all the stuff that was being done in various networking layers is now done all together in one protocol. So it's complicated. But and also TLS 1.3 is designed so that let's say it has a mode called 0 round trips. If I visited your server yesterday, I could say, hey, issue me a ticket so that tomorrow when I visit you, I can use this ticket to encrypt messages to you right from my first connection, from the first message, and simultaneously negotiate new material for my for the connection tomorrow, right? So with TLS 1.3 and Quick, you can get a 0 round trip latency at the level of UDP. The first message on a 3G network can send interesting application data. So there's a big push towards Quick. And Windows has an implementation of Quick, and we provide the crypto for the Windows implementation of Quick. And that's built on top of EverCrypt. And then I mentioned this Merkle tree, and that Merkle tree is in Azure's confidential framework. And then I mentioned Signal. The interesting thing about Signal is that Signal often runs in a web browser. So we actually now have a backend for this Kremlin compiler that instead of emitting C, it's the Signal protocol using EverCrypt in the browser. So broadly, I see as in this crypto space, I see that industrial grade verified crypto is now a reality. You can do it. We're doing it. There are other people in academia and other places doing it. MIT, folks at Amazon. We're able to build verified crypto at scale. I think there's in the open source community, especially, there's quite a lot of peer pressure to start moving towards verified. Certainly in the blockchain space, there's quite a lot of momentum in this direction. But also many hacks and so on that some of which look potentially malicious, things like the Snowden revelations and so on. I think there's a high degree of skepticism about implementations, and verification is becoming sort of necessary in some sense. I think maybe in about my guess, my prediction in some sense is that in the next, say, 5 years, unverified crypto will just be a liability in real software. Like you're just going to be required to use verified crypto. And there will be verified libraries that are just as fast and just as performant as anything else. So that's EverCrypt, okay? And then maybe in the last minute, I should just say a little bit about where F-star is going in general. This summer we worked on kind of doing separation logic in F-star. We see, overall I see it as doing this kind of proof at the level of F-star, but it's still more, the proof effort is still higher than we would all like it to be. And one of the main difficulties there is it's a classic problem in some sense. It's like reasoning about memory in imperative programs is the way the F-star methodology so far is based on what I've showed you so far is based on kind of problem that's from the tradition of languages like Daphne and so on, based on an idea called dynamic frames to deal with framing. But we're now trying to move towards doing concurrent programs and so on, and there we're working on a DSL that is trying to provide you with Rust-like programming in F-star using separation logic. So that's one thing that's happening. Does this have a name? We're calling it Steel. But that's just our name that we picked a couple of weeks ago, so it might change. Maybe we'll call it stainless steel. I don't know. And then I think broadly, a lot of this game is kind of finding DSLs where you can get proofs done with good automation. And EverParse is an instance of that. Vale is an instance of that. This Steel thing is an instance of that. Lowstar is an instance of that. I think there'll be many more of these. That's all I have. I also want to say I really enjoyed the last few days just lecturing here and also conversations in the halls and at lunch and over beer and so on. So it's been really fun. Thank you.